Hello everybody, I hope you're having a great ISW. Welcome to the second fundamental theorem of calculus video. Okay, so the first fundamental theorem of calculus that we looked at a couple weeks ago gives us a way to find the area under a function f of x on some interval from a to b by finding the antiderivative. So like, we've got some function that looks like this, and I want to find the area in between a and b. We know that that is the integral from a to b of f of x. And the first fundamental theorem of calculus tells us that if we can figure out the antiderivative of little f, let's say it's big F, then we just evaluate the antiderivative at b and then subtract the antiderivative evaluated at a. So the area under a curve is the net change in the antiderivative. However, we've also seen the tragic case in which we're looking at a function and we can't figure out its antiderivative. It just doesn't fit a pattern that we know how to integrate. So the second fundamental theorem of calculus gives us more of a conceptual way to figure out the antiderivative for functions that may not fit a pattern that we know how to integrate. So let's take a look. Okay, so let's talk a little bit about the theory and the concept of the second fundamental theorem of calculus. I've got a parabola up here on this graph. We do know how to find the antiderivative for a parabola, but let's just pretend that we didn't. So the idea behind the second fundamental theorem of calculus is that I am going to start integrating at 0. And then if I want to, so first we're going to talk about how would we find f of 3. So let me make sure we're clear on what all the notation means in this problem. So the graph that we're looking at here, this is a graph of little f of x. So this is the derivative. We are trying to figure out what capital F of x is, the antiderivative. And the first thing we're going to try to figure out is just the value of the antiderivative at a single value when x equals 3. So the way I might go about doing that is I'll start at 0 and I'm going to start shading in the area, and that's going to give me a sense of the net change from 0 to 3. So I'm going to shade an area from 0 to 3. I notice that at 0, the first slice of area here is negative area. So that means that capital F has to be decreasing, and it's decreasing by a pretty sizable amount. And then as I start shading over here, the slices of area are still going to be negative, but they're getting smaller and smaller. So that means that capital F, the antiderivative, is decreasing, but it's going to be decreasing by less and less as we move over. So I'm integrating, I'm now at 1. So in between 0 and 1, capital F has decreased by the shaded area here. I keep moving over here. Now I'm at 2. Capital F has started off as decreasing pretty quickly at 0, but now by the time we get to x equals 2, the derivative, little f of x, is now equal to 0. So that means that capital F of x was decreasing quickly and has now gotten to a point where it's about to turn because the derivative is switching from negative to positive. All right, so then as I continue to integrate, now I'm adding positive area. So that means that big F is going to be increasing. And then it's going to, and since each slice of area now is adding more and more, that means that capital F is going to be increasing faster and faster. So if we were to continue, we'd start to get something that looks like this. So if I knew the amount of the area I just shaded in, I could add the positive area, subtract the negative area, and that would tell me what capital F of 3 is. So capital F of 3 is equal to the sum of the area. And the process I just described is what this little equation down here is telling us. Capital F of x is, we just did the example where x is equal to 3. So f of 3 was equal to the integral from 0 to 3 of little f. And we just accumulated area. It started off as negative area and then positive area. And that's how the second fundamental theorem of calculus works. So notice that in this little equation, the bounds of integration has a variable in it. There's an x there. What that's saying is that if I want to find the value of the antiderivative at some particular value of x, I'm actually going to integrate from 0 up to that value, and then find the area underneath that. So you'll be able to recognize a lot of fundamental theorem of calculus, second fundamental theorem of calculus problems, because they have variables in one of the bounds of integration, or both of the bounds. But it's just this idea that we're accumulating area underneath the function. So how would you actually find this shaded area if you didn't know how to find it? So we're going to look at some examples of piecewise functions where we're going to be able to compute this area using just geometry or whatever. Here, if you didn't know how to find this area, you could use an estimation technique, trapezoidal rule, something like that. But don't worry about that. Okay, so let's look at some actual types of problems you're going to see. Okay, so that's the theory of the second fundamental theorem of calculus, that you are integrating over a certain range, and you can figure out what's going on with the antiderivative by looking at how much area you're accumulating as you move along. So in practice, there are two types of problems you're going to see. This type of problem is more of like a multiple choice type problem. It's one where you're just flat out asked to take the derivative of something that involves an integral. So here's a classic example problem. We're trying to take the derivative of a function where the variables are in the bounds of integration. So to see how we would do this type of problem, so we don't know what little f is. We don't have an equation for it. So what I'm going to do is I'm going to imagine integrating this thing, and then I'm going to take the derivative of that. So if I integrate this, I don't know what the equation is for little f, so I also obviously don't know what the equation for the antiderivative of little f is, but let's imagine it exists. I'm going to call it big F. So big F is the antiderivative of little f. So if I integrate, and I do this definite integration problem, then by the first fundamental theorem of calculus, I know I should get capital F of x squared plus 5x minus capital F of x squared. Right, so this is just the first fundamental theorem of calculus. I don't know what the equation for capital F is, but I know that if I did know the antiderivative, I could compute this definite integration problem by evaluating the antiderivative at the upper bound and then subtracting the antiderivative evaluated at the lower bound. Right? Does that make sense? I don't know why I'm asking this question, but I can't hear you. Okay, so that would be what we would get if we integrated. So now let's go ahead and take the derivative. So one thing to keep in mind is that since capital F is the antiderivative of little f, that means that little f is the derivative of capital F. So when I go to take the derivative of capital F of x squared plus 5x, when I take the derivative of the outside function, so the big F part, I'm just going to get little f again. So, but I'm going to need to use a chain rule because big F has a function inside of it. So the derivative of the outside function of big F is just little f. So we get little f of x squared plus 5x. And then we're going to need to multiply by the derivative of the inside, which is 2x plus 5. And then same thing when I go to take the derivative of the second term here. The derivative of the outside function is just going to be little f of x squared. And then, because I'm using the chain rule, I need to multiply by the derivative of the inside. So, that's the answer. you can generalize this process. There's an example on the next slide. So the general rule for the second fundamental theorem of calculus and these types of problems is, if you're given a problem where you're taking the derivative of an integral and the bounds of integration are some expressions involving x's, the lower bound is u, the upper bound is v. In the example we just saw, u was x squared and v was x squared plus 5x. The answer to this problem is you just plug in the upper bound into f and then multiply by the derivative of the expression v. Then you subtract, you do f of u times u prime. So here's an example for you to try. Go ahead and give you a second to give it a whirl and put your answer in play, pause it, and then I'll put the solution up here. Okay, so here's the answer. I just plugged in the upper bound for t, so you get little f of 3 to the x, and then you multiply by the derivative of the inside function. The derivative of an exponential is just natural log of the base times the original function, so this is the derivative of 3 to the x. Notice that when we plug in 0 for the lower bound, it's just going to disappear. That's because if you remember what we just did on the previous slide, okay, so this piece of the integral that we did, this is going to be a constant. I don't know what it is, but it's just a number. If we just plug a number into a function, we're going to get a number out. So f of 0 is just a number. So then when we go to take the derivative, this term's just going to cancel out because the derivative of a constant is 0. So in a case where one of the bounds is a constant, that piece of this formula is just going to go to 0. So that's why this piece goes to 0, and then for an answer you just get f of 3 to the x times natural log of 3 times 3 to the x. All right. Okay. So I think I'm gonna go ahead and put the other type of problem in a separate video so that we have time to do it. So, okay, we'll be back in a minute.